Alright, Part 7, Chapter 16, Solutions. Number 16 says, consider a saltwater solution, which is a solute and which is a solvent. The solute, in this case, since we have a solid dissolved in a liquid, the solute is going to be the salt, the solvent is going to be the water. All you have to do is think about what you dissolve in the water. The solute is what you're going to dissolve. You're going to dissolve the salt. Alright, let's 3 actions that can be taken that would help speed up the rate. This doesn't mean you're going to help get more dissolved. It just means you're going to get whatever you're going to get dissolved faster. So we could stir it, get it to dissolve faster. We could chop it up into smaller pieces and increase the surface area, and we can get it to dissolve faster. And finally, we could also increase the temperature, and that would make it dissolve faster. These two, 1 and 2, are not going to change the amount we get dissolved. 3 will, obviously. But 1 and 2 just speed up the process of actually dissolving it. Now it says most solids dissolve greater quantities in warmer solvents. Gases are the opposite. So normally the amount of solute dissolved will go up for solids. Let me put a little note here. These are solids. Most things get more soluble as the temperature goes up. Gases, however, do the opposite. Think about a flat soda. The warmer it gets, the less gas you have. So you might have points down here. It's flat. The colder it is, the more gas you have. So now we have points up here. So this curve would be for a gas. Okay. Alright, number 69, talking about saturated versus unsaturated. It says, when would a solution be considered saturated? And then how could you test to see if it is unsaturated? What could you do to determine the saturation point? Well, basically, if you didn't have a curve to look at, basically you would take a specific amount of substance, of solute, you drop it into your solution, and you look to see if it gets dissolved or not. If you add in a little bit more, and it actually dissolves, that means the solution you just had was unsaturated, because you were able to get more to dissolve. But if you drop in a little tiny bit, and it doesn't dissolve, and it sits at the bottom, then you know that you've hit the saturation point right before you added that little extra bit. So maybe add 30 grams and it all dissolves. Maybe add 31, it all dissolves. You add 32, it all dissolves. You add 33, it all dissolves. And then you drop in the 34th gram and it sits at the bottom. So 34 won't dissolve, but you know 33 did. So your saturation point is right there. Okay. Number 70 is basically looking at a graph and answering questions. A says the graph's based on 100 milliliters of water. Almost all solubility curves are. But what if you had questions regarding 1,000 liters of water? Forget about 100 milliliters. If that happens, or if you have 256 milliliters of water, or you have 3.5 milliliters of water, you set up ratios. You say whatever the graph says. You look at the curve and you figure out what the graph says, and the graph is based on 100 milliliters. And then you set up a proportion. You say, well, this is what the graph said in 100. What is it going to say if I had 1,000 milliliters? Or 1,000 liters in this case. Or what is it going to say if I had 250 milliliters? Or what's it going to say if I had 3,522 milliliters? So you can always set up proportions. As long as you know what the graph says, you can figure out an unknown based on how much new solvent you have. Alright, let's actually look at this curve here. It says, what's the maximum amount of K2Cr2O7 that can be dissolved at 50 and then at 90? So let's find the appropriate curve. It's this blue one over here. And then it says, what's the max amount we can dissolve at 50 degrees? So let's go to 50 degrees. The maximum amount is right on the curve here. Right there. So it's about 30 grams. We can get 30 grams to dissolve, no more though. If we try to dissolve more, it'll be over the curve and that much extra will sit at the bottom. But yet if we heat it up, we go from 50 all the way up to 90. Now this curve goes way up here, and now it's probably 68 grams. We can get more to dissolve. Alright, imagine you had 70 grams of CaCl2, 100 grams of water. This just means you can use the graph as is, and you're at 0 degrees Celsius, so you know where to look. So we're here, 0 degrees. We had 70 grams. Let's put a little mark right here. And we're dealing with CaCl2, which is this kind of orange curve right below it. To what temperature must this be heated to get all of it to dissolve? So we're at 0. We have 70 grams. Let's go over, right here. that's where it's going to hit the curve, that's where it dissolves. Go down and, I don't know, maybe 16? About 16 degrees Celsius, we can get it to all dissolve. Letter D. Imagine you had 60 grams of NaCl in 100 grams of water. That just means we can use the curve as is. We don't have to set proportions. And it's at 100 degrees Celsius. So here we go. 60 grams of NaCl. So let's go to 60 grams. Let's go to 100 degrees. Put a mark right there. Then it says how much will remain at the bottom of the container. So that means we have excess. Now normally at 100 degrees we should only get about 40 to dissolve. This is saying we dumped in 60. Do the math, figure out the difference, and 20 grams is going to sit at the bottom. Letter E. Oops, I don't want to lose the graph here. Alright, letter E. What kind of solution with 30 grams KNO3 and 100 grams of water? Again, we can use the curve just as it is. 30 grams KNO3 at 40 degrees. So here we go, 40 up to 30. And it looks like we're below the line here. We could go all the way up to right about here. So right about 60, I don't know, maybe 64 grams. Again, as long as you're in the ballpark, we're okay here. Now this is how much we dumped in, 30. But yet we could dump in all the way up to 64. So it looks to me like we're way below the line, so that's unsaturated. Unsaturated. And the last graph. Imagine 50 grams of NaNO3 is added to 100 grams of water. Nice, last problem. We still haven't used a ratio. At 10 degrees. So 50 grams at 10 degrees. Let's go find where that point is. 10 degrees, 50 grams. Put a little circle right there. How much more NaNO3 could be added and dissolved at this temp? So we're going from 50 all the way up to 80, because that's where it hits the curve. So 50 from 80 is 30 grams. You could add 30 grams more and get it to all dissolve. You have add 31, you're out of luck, but you could add up to 30. All right, calculations. Molarity. Molarity is basically saying how many moles can you add in to how many liters. And when you divide through by a number on the bottom, you're going to end up with number of moles if you had 1 liter. Remember, we always use the density formula. We always try to get 1 milliliter or 1 cubic centimeter or 1 whatever on the bottom. And then it tells us the mass in grams that that volume would take up. We're doing the same thing here. So calculate the molarity of a solution. We got 3.4 moles. That goes on top. And we have 3 liters on the bottom. Nice easy setup here. And when we do the math, we end up with 1.13, and then in chemistry you put a big gigantic M there, and that means it's a molar solution, and that's what we say, a 1.13 molar solution. Okay. Calculate the molarity. Now we have grams, not moles. You can't just go stick grams on top. You have to get moles first, but you all know how to do that, hopefully. 65.3 grams times, grams goes on the bottom. We got to convert to moles, so put moles on top. And then we know that if you look at the periodic table and add them up, 1 mole is 58.5 grams. Grams cancels out, you get moles, and we end up with 1.12 moles, which is good because now we can put that on top, 1.12 moles. We got moles, and we know that's how many moles we would have if we had 2.5 liters. Let's divide through and figure out how many we would have if we had only 1 liter. Final answer, 0.45, big capital M, 0.5 molar solution.